Welcome back to optimization. So, as instructors, we distinguish problems as level 1 and level 2 problems. So while level 1 problems are optimizations problems where the function is given, in level 2 we denote problems where the function is not given and needs to be constructed. So here I give you a very typical level 2 problem for optimization. I remind you of our saying, you draw names for max and min, where u means to understand the problem, find the known and unknown variables, draw, and here we will see that the graph is actually quite important. Give names to all the variables, find a formula for whatever needs to be optimized, and then do it. Maximize or minimize. So here's a problem. It is about a seed storage. So assume you're designing a cylindrical silo that can hold 24,000 liters of seeds. So not liters, but liters of seeds. You need to manufacture the base, the sides, and the lid from metal, but sheet metal is expensive. What are the dimensions of the silo that minimizes the cost of the metal? To understand the problem, we see what we've got. So the total volume is 24,000 liters. We know that the form of the silo is a cylinder, but we don't know the radius r or the side h. Names, so we call the radius r, we call the height h, the base, the area of the base we call maybe b, and then the lid will have the same area, so we call that also b, and then the sides have an area of s, and the total surface area would then be a, and the total volume would then be v. And of course the total area is the sum of b plus s plus the bottom b. But this comes later in the formula section. So here are the formulas. Let me introduce my b's again. These were those bits. And the s is the outside mantle. Now 24,000 liters are 24 meter cubed. Then the base has an area of pi r square, as does the lid also. And the sides have an area 2 pi r times h. So the total area is 2b, which is base plus lid plus the mantle around it. And then the volume is given as pi r squared times the height h, and this has to be 24 meter cubed. So let's simplify. What do we want to optimize? Well, we want to optimize the area, right? Because the area is proportional to the amount of sheet metal which we need. But the area can be written as 2 pi r squared plus the side, which is 2 pi r times h. So now we get a function which depends on the radius and on the height. Of course, it should. But by the volume constraint, we have one more equation which we can use to replace r or to replace h. So I use to replace h because it seems to be a bit simpler. So we know that pi r squared times h is equal to 24. So then I solve this for h, and this makes h to be 24 divided by pi r squared. And now I take this and sub it in here. So then I get a equals 2 pi r squared plus 2 pi r, and then replace h with a 24 divided by pi r squared. And then I can simplify a few things. I keep the 2 pi r squared. Now the 2 multiplies with the 24, it gives a 48. The pi cancels with the pi, 1 r cancels with 1 r, so then we get 48 divided by r. So now this is a formula a of r, which only depends on one variable r and no longer on two. We have one equation for the area which depends on the radius, so now we can optimize. Yippee! Let's go right to it. So max or min? Of course we want to minimize the area. So how do we do this? We look at the domain first. Now the radius of the cylinder can't be 0 because then there is no cylinder, so it's away from 0. But otherwise, we really don't know how large it can be, so the domain is 0 to infinity. Okay, and then let's look at the critical points. So we need to build the derivative, a prime of r, which is 4 pi r minus 48 divided by r square. And then critical points satisfy a prime of r is equal to 0, which means 4 pi r is equal to 48 divided by r squared. So then we can multiply with r squared and divide by 4 pi. Can you do this in one step? So then we have r to the 3 equals, now 48 divided by 4 is 12, and then we still divide by pi, so we have r cubed equals 12 divided by pi, so r is equal to third root of 12 divided by pi. So that's our critical value. So we found the critical point, and we have a domain from 0 to infinity, so we have to make sure if this is a minimum or a maximum. And in this case I use a second derivative test. So meaning I differentiate again. I have written a prime right here, so then a double prime of r would be 4 pi plus 48 times 2 divided by r to the 3. And then this is positive for positive values of r. That's all I need, because then I know that at r is equal to third root of 12 over pi is a local minimum. And also an absolute minimum, since there are no other critical values in this open domain. Perfect. Let's see what this is. So r is about 1.56 meters. And then the height, we still had the formula for the height from earlier, which is 24 divided by pi r square. So sub in r square to be 1.56 square. And then this gives you 3.126 meters high. So that's the dimension of your cylinder if you want to put in 24 cubic meters of seeds. Let me summarize a bit. We were guided by our saying, you draw names for max and min. It was important to replace one unknown h with another unknown r to get a function that only depends on one variable a of r. Now, here you could have chosen differently. You could have replaced r by h, and then you get a function which depends on h. Same story should also work. Now, these kind of geometric optimization problems are quite typical in calculus. So building cylinders or building boxes or building fences around square domains is typical. And oh, what a surprise! What do we have here? A beautiful cylindrical box. I bet you it has been designed for an optimal volume. Let's look inside.